Good morning. We are going to do our first online recitation today, and I hope it will be useful for you. And I think you all covered the lectures that is posted by Mustafa Korkmaz on YouTube related to set of subgroups and the beginning of ring theory. Okay, please, while I'm talking, just unmute yourself, and if you have any questions, please mute. No, first mute yourself, and if you have any questions, just unmute yourself and ask your question. Okay, do not hesitate to interrupt me while I was solving the questions. I think you all reviewed the content. So let me start with my first question about Sylow theorems. This is online recitation 1. Okay. Then, please, if you have any problem in seeing the screen of the tablet, please let me know, and I'm going to try to fix the problem. Now, our first question is, let G be a group of order 12. Show that G has a normal subgroup of order 3 or 4. 3 or 4. Okay, before that, do you want to make these online sessions interactive? If you want this thing, then you can just all unmute and try to participate in class. Okay, just for example, what is your opinion about this question? If you have a group of order 12, how can we show that it has to have a normal subgroup of order 3 or of order 4? How you can do that? Any suggestions? Okay, you can talk in Turkish, and okay, Janet, you're saying that my voice is not coming. Any problems about voice, or is it just a problem because of Janet's computer? I don't know. Is everybody able to hear me? No? Evet. İrem, does it mean that there's no problem or what?
No.
No, okay, you can hear me, no problem.
Yeah.
Okay, Jenna, could you please your connection about microphones or your headphones, I don't know. And if the problem is solved, please let me know. Okay, by this time, any opinions about the problem? Okay, let me start with decomposing the order of G. We have the order as 12, which is 2 to the 2 times 3. So we are going to look at Sylow 2 and Sylow 3 subgroups of the group G. Okay, by Sylow theorems, what we know is that about the number of Sylow subgroups by Sylow theorems, we know that N2 divides 3 and N2 has to be equal to 1 modulo 2. What is N2? For an arbitrary P, where P is a prime number, and P means that the number of Sylow P subgroups. Sylow P subgroups of G. Okay, so if we consider the number of Sylow 2 subgroups, I said with Janet again. Okay, if we consider the number of CELO2 subgroups, then it has to divide 3, and it has to be 1 modulo 2. Okay, and what about N3? N3 should divide 4, and N3 has to be 1 modulo 3. Okay, so what we have for N2, we have the possibility which is equal to 1 or which is equal to 3, because it has to divide 3 and has to be 1 modulo 2. And for N3, the divisors of 4 is 1, 2, and 4. So this means that since it has to be 1 modulo 3, it has to be 1 or 4. Okay, here 1 or 4. Okay, so if here, let us consider, try to consider all possibilities. If N3 is equal to 1, then this means that CELO3 subgroup, if P is CELO3 of G, this is the set of CELO3 subgroups of G. This means that this CELO3 subgroup is unique, and hence, no, P is the unique CELO3 subgroup, CELO3 subgroup, and hence it is normal. And hence P is normal in G. Okay. Do you know why? If you have a unique CELO3 subgroup, then it has to be normal. Can you explain me why? Why a unique CELO3 subgroup is normal? Any opinion? Any suggestion about this one? Nope. Okay, I think it is covered in the lecture notes. And if you relook, rewatch the video, then you can see that all CELO3 subgroups are conjugate to itself. So by this reasoning, you can say that a unique CELO3 subgroup is always normal. Okay, and if it is normal, then it has to be unique. So let us note this here. Note a CELO3 subgroup. P subgroup is unique if and only if it is normal. Okay? Just as an exercise, you can prove it again. Okay. Then, in this case, we have found actually a normal subgroup of order 3. Why is that so? Because 3 is a prime dividing the order of G, and the power of 3 in the order is 1. So this means that the order of P, the CELO3 subgroup, is equal to 3, and P is normal in G. This means that in this case, we have found a normal subgroup of order 3. Okay, what about the other possibility? If n is not equal to 1, but n3 is not equal to 1, but n3 is equal to 4. Now assume that, because we have to cover all the possibilities, assume that n3 is equal to 4. In this case, this means that we have 4 different CELO3 subgroups. Then there are 4 CELO3 subgroups of G. Since CELO3 subgroup is not unique, then this means that these CELO3 subgroups are not normal, okay? And so these subgroups, here I'm adding another, okay, I'm adding another page. These subgroups are not normal. are not normal. Are not normal. But in this case, how many non-identity elements of order 3 we have? Okay, let me take first two Silo 3 subgroups. Oops. Let P1 and P2 be two different Silo 3 subgroups of G. Now, what can we say about the intersection? Then P1 intersection P2 has to be trivial. Why is that so? Because we know that P1 intersection P2 is a subgroup of P1 and a subgroup of P2, of course. And by Lagrange theorem, we know that the order of P1 and P2 has to divide the order of these Pi's. Okay, I is equal to 1 and 2. And in this case, we know that this order is equal to 3 because Pi is a Silo 3 subgroup. Okay. So this means that the possibilities for P1 intersection P2 is equal to 1 or 3. But we have said that P1 and P2 are different Silo 3 subgroups, as P1 is different from P2. This means that P1 intersection P2 cannot be equal to P1 or cannot be equal to P2. P1 intersection P2 is different from P1, oops, P1 and P2. So this implies that this intersection P2 has order 1, okay? And this means that if you have two different Silo 3 subgroups, then the intersection of these two is always of order 1, okay? So from here, since we have 4 different Silo 3 subgroups, if you want to count the elements of order 3 here, from each we are going to have 2 non-identity elements. We have 4 Silo subgroups, Silo 3 subgroups, and we have 3 minus 1 non-identity elements. Non-identity elements of order 3. And this means that 4 times 2, we have 8 elements of order 3 here. Okay, we have reached eight elements of order 3. Then this means that we are left with 2 minus 8. We have 4 elements left. Okay, and since we have counted all elements of order 3, and these 4 elements should belong to Silo 2 subgroups, okay? Because we know from the existence that since 2 is a divisor of the order of finite group G, then this means that Silo 2 subgroups exist. And this means that these 4 elements has to belong Silo 2 subgroups. Subgroups. Okay, and if you let now Q is a Silo 2 subgroup of G, then we know that the order of Q has to be equal to 4, and we have only left with 4 elements. So this means that since there are only 4 elements left, they have to they all have to belong to Q. And this means that there is only one Silo 2 subgroup. This means that Q is the unique Silo 2 subgroup. Hence, Q is normal in G, and the order of Q is equal to 4. So in each case, whether first in the case of here, and 3 is equal to 1, we have found a subgroup of order 3 which is normal. And in the other case, where is it? In the other case here, and 3 is equal to 4, we have found a subgroup of order 4, which is normal in G. Okay? So if you have a subgroup of order 12, you have either a normal subgroup of order 3 or a normal subgroup of order 4. Okay? Any problem? Any question? Anything that is not clear to you? Okay. Okay, let us continue with our second question. It is a little bit harder. Okay, let's now G be a group of order 231. Now prove that every Sylow 11 subgroup of G is contained in the center. Is contained in the center of G. Center of G, which is denoted by Z of G. Okay? First, let me decompose this 231. This is 3 times 7 times 11. It is hard to write on a tablet. Okay, now we are going to consider Sylow 11 subgroups, and we are going to show that those Sylow 11 subgroups has to be contained in the center. Okay, now first, what can we say about the number of Sylow 11 subgroups? Okay, now an 11 has to divide 21, and an 11 has to be 1 modulo 11. Okay, then what are our candidates for an 11? 1, 3, 7, and 21. But it has to be 1 modulo 11. No, this is not an implication for sure. Okay, 7. So consider this modular equality. So in this case, the only possibilities are 1 or 20. No, it is 1. No, it has to be 1, of course. This is 21 because of this modular equality, and 11, that is the number of Sylow 11 subgroups, has to be equal to 1. This means that if P is P11, let me call, just P, P Sylow 11 of G, since and 11 is equal to 1, this means that P is a normal subgroup of G as P is unique. Okay? So we have only one Sylow 11 subgroup of G. Okay, in this case, it is normal. So we are going to talk about a group action of G on the Sylow 11 subgroup P. Okay? Now G acts on P by what? We have a normal subgroup, and what can you say about this action? What is the natural action of G on the Sylow P subgroup, normal Sylow P subgroup P? What is the natural action? Huh? Okay, of course, the natural action is conjugation. Because since we know that P is a normal subgroup, it has to be invariant under the conjugation, right? So what does it mean? This action means that there is a homomorphism phi from G to automorphism group of P or symmetric group of P, doesn't matter. Then this means that you're actually seeing the elements of G as the automorphisms of P. And since the action is conjugation here, this means that we are taking G to some phi sub G. And what does this phi sub G does? Phi sub G is a map from P to P because G acts on P, and taking an element H here to what? G, P, G inverse. Okay? That's good. G, H, G inverse, of course. Okay? So, what can you say about the automorphism group of P? Now, we know that P is of order 11, right? And this means that since every group of prime order is cyclic, this means that P is isomorphic to Z11. And what can we say about the automorphism group? Now, automorphism group of Z11 is isomorphic to Z10. This means that automorphism group of P is of order 10. Okay? Now we have a homomorphism from G to automorphism group of P, which is a group of order 10, a cyclic group of order 10. And then since we have a homomorphism here, we can apply first isomorphism theorem. By first isomorphism theorem, we know that G over kernel phi is isomorphic to a subgroup of automorphism group of P. This means that isomorphic to a subgroup. Okay? Now, this, or you may see this one as a subgroup of automorphism of P, and using Lagrange theorem, you can say that the order of G over kernel phi divides the order of automorphism group of P. Okay, now what we have is that since we can see this quotient as a subgroup of automorphism group of P, this means that order of G over kernel phi has to divide the order of automorphism group of P. And we know that this is the automorphism group of that 11, and this means that this is the order of that 10, which is equal to 10, okay? But we have the order of G as 3 times 7 times 11. Now this means that this quotient, the order of this quotient is something related to 3, 7, and 11, right? So what can you say about this one? Is that since the kernel, this kernel quotient should divide 10, but we have all numbers in the decomposition of the order of G is relatively prime to 10. This means that this quotient has to be equal to 1. Okay, because there is no divisor of the group of the order of the group G, which divides 10, right? So this means that this quotient has to be equal to 1. And this means that G has to be equal to kernel phi. And what does it mean? This means that every element of G acts like an identity map on the group P, on the CeLO 11 subgroup P. So this means that phi sub G from P to P, taking H to G, H, G inverse is the identity map. Identity map for every G in G. Okay? And this means that G inverse is equal to H for every G in G for every H in P. And this gives us that H commutes with every element in G. Every element of P, commutes with every element in G. Hence, and so every element in P lies in the center of G. Okay? So since every element lies in the center, this means that P lies in the center of T. Any problem? This was a little bit harder from the first one. Do you have any problems? Any questions? Okay, if you have no comments on this question, then we are going to continue with another one. Now a group of order 217, yes, is, nerede? 217 is cyclic. Now we are going to show this one. If you have a group of order 217, then it has to be cyclic. Okay. It has to be cyclic. Okay. Now let us first decompose the group order. 217 is equal to 7 times 31. And now what can we say about the number of seed of 7 subgroups? Now N7 has to divide 31, and N7 has to be 1 modulo 7. And this means that since 31 is a prime number, we have only 2 possibilities for N7, which is 1 or 31. But since it has to be 1 modulo 7, this means that we have only one possibility. We have only one possibility, and 7 is equal to 1, okay? Using these two relations. Okay, do the same thing with N31. It has to divide 7, and it has to be 1 modulo 31, okay? Now, for the possibilities of this one is 1 or 7, but since it has to be 1 modulo 31, this means that 7 cannot be a possibility. Then this means that the number of CELO 31 subgroups is equal to 1. So P7, which is a CELO 7 subgroup, then it has to be normal in G, and P31, which is CELO 31 subgroup, this is again normal in G. Okay, now we have 2 normal subgroups inside the group G, and what if we consider the orders here? The order of P7 is equal to 7, and the order of P31 is equal to 31. Now, what can we say about the intersection of these two? Now, the intersection P7 intersection P31, if you consider this one, this is the subgroup of P7. This means that the order of P7 intersection P31 should divide 7. And in this case, the possibilities for this one is 1 or 7. But on the other hand, P7 intersection P31 is a subgroup of P31. So by Lagrange theorem, we know that P7 intersection P31 divides the order of CELO 31 subgroup, which is equal to 1. So here we have the possibilities 1 or 31. But since 7 and 31 are relatively prime, the only possibility for the intersection, here, P7 intersection P31 is equal to 1, as 7 and 31 are relatively prime. Okay, so now what we have is that we have 2 normal subgroups here with the trivial intersection here, and if we consider the product of these 2 subgroups and the order here, if you remember, we have proven that the order of this product subgroup is the order of P7 times the order of P31 over the intersection. And this means that the order of CELO of 7 subgroup is 7. The order of CELO of 31 subgroup is 31 over the intersection is trivial. So this is exactly the order of our group, okay? So we have P7 and P31 as normal subgroups of G, and P7 intersection P31 is trivial, the intersection is trivial, and the order of the product is equal to the order of G. This means that you're going to apply external direct product here. G is isomorphic to P7 times P31, okay? And also note that here, since the order of P7 is equal to 7, P7 is isomorphic to that 7. And since the order of P31 is equal to 31, P31 is isomorphic to cyclic group of order 31. 31, okay. So this means that this group is actually isomorphic to that 7 times that 31. Since 7 and 31 are relatively prime, this means that this is isomorphic to that 7 times 31, which is that 217, okay? So we have our group here, it's at, finally, it is isomorphic to a cyclic group of order 217, okay? Hence, G is cyclic of order 217, okay? Any problem? First, we have considered the number of Silo 7 and Silo 31 subgroups, and we have found that they're all normal. And after looking at the intersection as a trivial one, and computing the number of elements in the product subgroup, we have found that we have formed G as the direct product of these two subgroups, and finally, we have found that G is isomorphic to the cyclic group of order 217. Okay? Any problems? Anything not clear? Okay. So another, okay, maybe we can skip this one. I don't know. Okay. Now let G be a non-abelian group of order P times Q, where P, Q are primes with Q is congruent to 1 modulo P. Okay, now we are going to prove that G has a normal subgroup of order Q. There is a normal subgroup of order Q, and the number of Silo P subgroups of G is what? Q. Okay, any suggestions? No. What a nice interactive online recitation. Okay, no suggestions, no comments. Okay. Okay. Now, what can we say about the number of Silo P subgroups? This is 1 modulo P, and NP has to divide Q. And if we consider the number of Silo Q subgroups, this has to be 1 modulo Q, and NQ has to divide P, okay? Now what we have using this condition, since Q is equal to 1 modulo P, this means that Q is a prime which is greater than P, right? So this means that by using this one, NQ has to be equal to 1, okay? So Silo Q subgroups, Silo CELO Q subgroup is unique, and hence normal. Let me give a name Q here, normal, and we know that the order of Q is equal to Q, and we have found a normal subgroup of order Q inside G. Okay. Now, what about the other thing? The number of CELO P subgroups of G is Q. Okay. Now, here, from these relations, we have NP is either 1 or Q. We don't know which one. Now, if NP is equal to 1, then the CELO P subgroup, subgroup P is normal in G, and the order of P is equal to P. Okay, but in this case, by the same thing that we've done in the previous question, by the same idea in the previous question, we have G as cyclic of order P times Q, okay? Because we have a normal CELO Q subgroup of order Q, a normal CELO P subgroup of order P. Each of these is isomorphic to cyclic groups, and P and Q are prime, so they are relatively prime with each other. This means that we can write G as the direct product of these two. So at the end, we have found that G is isomorphic to the cyclic group of order P times Q. But in the question, it is given that G is not abelian. So this means that this is the contradiction. As G is non-abelian. And hence what we have, NP is equal to 1, our assumption NP is equal to 1 is not true. Hence, NP has to be equal to Q, so we're done. Okay? Any questions? Okay, this was an easy one. Now our last question with CELO theorems. I don't know whether our time will allow us, but let me try. Now a group of order 72 is not simple. What is a simple group? Do you remember? Do you remember what the simple group is? What a simple group is? Okay, let me remind you. A group is simple. Is simple if the only normal subgroups are the identity subgroup, and the group itself, Okay, this is as a reminder to you. Okay, here we have a group of order 72, and we're going to show that it has no non-trivial normal subgroups. Okay, now if we have a group of order 72, which is 2 to the power 3, 3 to the power 2, and we can consider CELO 2 subgroups and CELO 3 subgroups. Okay, now consider the number of CELO 3 subgroups. This has to be 1 modulo 3, and N3 has to divide 8. Now, in this case, the possibilities for this one is 1 or 4, because the divisors of 8 is 1, 2, 4, and 8, but it has to be 1 modulo 3. This means that we have only 2 possibilities, N3 as 1 or 4. Now, if N3 is equal to 1, then this means that there is a unique CeLO3 subgroup. Okay, are we all here? Ahmed, maybe it is about my connection or your connection. I think there is no problem with my connection, but I'm going to try to fix it if there is any before the second session. Okay, let me complete this question, and we're going to take a break. Okay, break of 10 minutes. Okay, now if we have only one CeLO3 subgroup, then there is a unique CeLO3 subgroup, and hence it is normal. No, you cannot see my screen. Okay, here. Okay. Now, if N3 here, N3 is equal to 1, the CeLO3 subgroup is unique and hence is normal. Normal. This means that we have found a non-trivial normal subgroup of our group G. So we are done. We are done. So assume that N3 is equal to 4. N3 is equal to 4. Okay. Now, CeLO, then CeLO3 subgroups of G are not normal because they're not unique. So we have to find a non-trivial normal subgroup of G, okay? Different from identity, different from itself. Okay, now let us consider here CeLO3 of G. This is the set of all CeLO3 subgroups of G. Now G acts on this set, CeLO3 G. Okay, since we know that all CeLO subgroups, CeLO-P subgroups are conjugate to itself and vice versa, this action of G on this set is by conjugation. And since we are now in the case of N3 is equal to 4, the size of this set is equal to 4, okay? And this means that there is a homomorphism phi from G to symmetric group of this set, CeLO3 G, okay? And since we have said that the size of this set is equal to 4, then what can we say about the size of this group, the symmetric group of this set? And actually, since we are considering symmetric group on 4 letters here, this is isomorphic to, no, this is isomorphic to S4. So our homomorphism actually, phi, is from G to some kind of S4, okay? So what can we say about, what can we say about the kernel of this one? We are going to make use of first isomorphism theorem again. By first isomorphism theorem, okay, G over kernel phi is isomorphic to a subgroup of S4. And this means that if you consider the order here, the order of S4 is equal to 4 factorial, which is 24, 2 to the power 2 times 3. No, 2 to the power 3 times 3. And so this quotient has to divide this 24. Okay? But we know that the order of G is equal to 72, which is greater than the order of S4, which is equal to 24. So we have to have something in the kernel. Kernel phi is non-trivial. Okay? because of this division, okay? Something related to 72 here has to divide 24. So this means that we have to have something in this quotient, okay? But now we know that every kernel is normal. But one thing remains to show that kernel is different from, this is different from identity, but we have to show this part also, okay? Now, if kernel phi is equal to G, then this means that G, P, G inverse, since the action is conjugation here, and the kernel is the whole group, then this means that all elements of G act like an identity map. This means that G, P, G inverse is equal to P for every G in G, and this means that this P, a CELO what subgroup? CELO 3 subgroup is normal. P is a normal. P is a normal CELO 3 subgroup, which is not the case. It's not the case because we have 4 of them. Okay, so we obtain a contradiction here. So this means that kernel phi is different from G, kernel phi is different from the trivial subgroup, and kernel phi is a non-trivial normal subgroup of G, so G is not simple. Okay, any problem? Any questions? Okay, now we have completed our first session. I'm actually recording the lecture. I'm going to publish it. Maybe send you a link via Outlook. Okay, let us continue in 10 minutes with the second session. Okay, see you. Now I'm ending the meeting, the first session. Okay, see you in 10 minutes. Okay. Now, in the second session, we are going to start with some questions related to the beginning of the ring theory, okay? Now, suppose that R is a ring with A squared is equal to A for all A in R, okay? Such kind of rings are called Boolean rings. Boolean rings, okay? Now, as you know that rings are a little bit different from the groups. We have 2 operations here. One is called addition, and the other one is multiplication. And with addition, with the first primary operation, our ring is actually an abelian group. And the multiplication only satisfies associativity, and these 2 operations is linked via the distributive law. Okay, now in this question we have a ring R satisfying A squared is equal to A for every A in R. Now first we are going to show that. And after that, show that A plus A is equal to 0 for all A in R. Okay? Any opinions? Any suggestions for this one? Okay. No, let us first consider A plus A. Okay. Okay, mute all of you. Okay. Okay. And if you have any questions, please interrupt me and ask your questions. And now consider A plus A and take the square of this one to make use of this identity inside our ring. Okay. Now we know that the square of any element in this ring is equal to itself. A plus A squared is equal to A plus A. Okay, now if we apply the multiplication here, what we have is that a squared plus a what? A squared, what is this? Okay, let me apply this one. A plus a times a plus a, which is equal to a squared plus a squared plus a squared plus a squared. I noticed that I solved wrongly in my notes. Okay. Now what we have is that instead of, and we know that this is equal to a plus a, okay, from here. Now what we know is that, what is this? Each a squared is equal to a, right? Because of this equality. Now we have a plus a plus a plus a is equal to a plus a. Then by cancellation, what we obtain is that just adding each side the additive inverses of a, minus a plus minus a plus a plus a plus a plus a is equal to a plus a. Then from here, we have 0 here, 0 r plus a is equal to a plus, no, I did something wrong. Here, of course, you're going to add the same thing here. Minus a plus a plus a. We have 0 here and we have 0 here. So at the end, we have a plus a is equal to 0. And a was arbitrary, so we obtained our equality. As the second question, second part of this question, show that R is commutative. Commutative, the word commutative is related to the multiplication. Okay, now this means that for every AB in R, we are going to show that AB is equal to BA. Okay, for this one, let us consider the square of A plus B. A plus B squared. Okay, this is equal to, if we apply the multiplication. Now, since with respect to multiplication, we don't know whether ring R is commutative or not. We have to apply the multiplication, preserving the order of elements, okay? A plus B times A plus B is equal to A squared plus AB plus BA plus B squared, okay? And since we know that the square of every element is equal to itself, this is equal to A plus B. The square of A plus B is equal to A plus B, okay? Let me see, okay. Now this means that here we have A squared, which is equal to A. Here we have B squared, which is equal to B. We have AB here. So A plus AB plus BA plus B is equal to AB. Now applying the cancellation, but by the additive inverse of A from left and the additive inverse of B from right, we obtain that AB plus BA is equal to 0. And from here, we get AB is equal to minus BA. But what we are going to do with this minus? Now, go back to the first part. Here, we have found that A plus A is equal to 0, right? By part A, what we have is that A plus A is equal to 0, and this is if and only if A is equal to minus A for every A in R. So this means that here, this minus sign does not mean anything. So here, AB is equal to, let me put a star here. By star reasoning, AB is equal to BA for every AB in R. So the multiplication is commutative, meaning that your ring R is a commutative ring. Okay? Any questions? Nope. Okay. What about this? What about subrings? Subrings. Okay, now let R be a ring and S be a subset of R. Okay, now we're going to call S as a subring of R. S is a subring of R if the following holds. This is also covered in the lecture video, in the second lecture video. The first one is x minus y lies in S for every x, y in S. And secondly, x times y lies in S for every x, y in S. Okay? Now, as an example, as our next question, let R be the ring of all 2 by 2 matrices with integer coefficients. Now consider the following subsets. Consider the following subsets. The first one is S, which is consisting of elements which, here, S. We have some elements in the off diagonal, S and Z. And as the second one, consider the set S prime, for example, and we have S's in the diagonal. Okay, now our question, of course, is that which one is a subring, which one is not, or both of them are subrings, or none of them are subrings. Determine which one is a subring and which one is not. Okay? To say that a subset is a subring, we have to satisfy these two conditions. And to say that it is not a subring, then we have to fail one of these conditions, okay? If you consider the first one, do you have any idea? Any suggestions? No? Any suggestions? Okay. Then, for example, I'm going to consider the first one, okay? Let us take two matrices. 0S, 0S is B, no. 0S, 0S, S0 is A, and B as 0, T, T0, such that A, B are different, and okay. I'm going to show that the first one is not a subring, so let me take some concrete explicit examples. 1, 1, 0, and B as 0, 1, 0, no, 1, 0, okay? From where? From S. From S here, okay? And if you consider the product of these two, 0, 1, 1, 0, times 0, 1, 1, 0, then what we get is that 1, 0, 0, 1. And this is not of type elements in S, right? So this is not in S, meaning that S cannot be a subring of R. S is not closed under multiplication. So S is not a subring. Okay? What about the second one? The second one is consisting of all matrices with coefficients, with the same coefficients on the diagonal. Okay, let me first justify the first condition. Let us take, let's A S0, 0, S and B T0, 0, T. No. Here. Okay. B in S. B in S. Then for the first one, we are going to look at whether the difference of these two lies in S or not. Okay. Okay. Now we are back. Okay, for this one, we are going to, where's our screen? Here. Okay, minus T0, 0, T, and this is, again, gives us an element of the same type, and this lies in S, meaning that S contains all differences, okay? For the second one, A times B is equal to S0, 0, S times T0, 0, T. This gives you S times T, 0, 0, S times T, and this is, again, an element from S, meaning that we have covered, okay? So this means that we're sharing, right? We're sharing. Okay. Am I sharing the screen? Can you see it? Yeah, now. Okay. Now this means that two conditions are satisfied, hence S prime is a subring of R. Subring of R. Okay. Now we have two examples of a subring and a non-subring for the ring of 2 by 2 matrices with integer coefficients. Okay, so to justify that a subset is a subring, then it has to be it has to satisfy these two conditions. Okay, now our last question is that prove or disprove the following. The first one, the intersection of two subrings of a ring R is a subring. Is it true? The second one, the union of two subrings of R is a subring. You can just write it on chat. Do you have any opinion? The intersection of two subrings is always a subring of R. Is it true? Or the union of subrings is a subring. Is it true? Do you have any idea? Okay, girls, no ideas. The first one, actually, the first one is true, and the second one is false. Okay, the union of two subrings need not be a subring. Let us consider a counterexample here. Let R be the ring of integers. Very basic example. Integers, Z. Okay. Now take the subrings 2Z and 3Z. Okay. And if you take the union of these two subrings, is it a subring? Is a subring. Our question is this one, right? For our particular example, if you consider 2 from 2z and 3 from 3z, and if you add them up, we have 5. If this were a subring, then 5 had to be included in this one, right? In this subset. But this does not lie in 2z union 3z. So this means that this is not a subring. Okay, because 2z contains all integers, all even integers, and 3z contains all integers, which are multiples of 3. So the union of these two is not a subgroup. What about the first one, the correct one? Now let R be a ring and S and S prime be subrings of R. Now we are going to show that S intersection S prime is a subring. Now for the first one, let X and Y be two elements from the intersection. Okay? Now show X minus Y is in S intersection S prime. Now since X and Y are taken from the intersection, and this means that X is in, no, XY, if you consider these two sets separately, since these two are in the intersection, XY is from S and XY is from S prime, okay? Now, since S is a subring, X minus S, X minus Y lies in S, and similarly, since S prime is a subring, X minus Y is an S prime. So this means that X minus Y lies in the intersection. Okay, so we have covered the first condition. The second condition is similar. XY lies in S means that X times Y is in S, as S is a subring. And XY lies in S prime means that XY is in S prime, as S prime is a subring. And so XY lies in S intersection S prime. So what we have is that X minus Y is in S intersection S prime. Just last sentence, okay? X times Y lies in S intersection S prime. Two conditions are satisfied. This means that S intersection S prime is a subring. Of R. So as you can see from the beginning, the union of two subrings need not to be a subring, but the intersection of subrings is always a subring of R, of the ring R. For an arbitrary ring, for arbitrary subrings, and this is all. This is all for today's recitation, okay? Do you have any questions? Do you have anything to ask about the questions that we have solved today? I'm going to edit this this page to a PDF file, and I'm going to put it on AutoClass or MetaClass, whatever it is. And also, I'm going to try to add the video version. Okay, if you want to review from the video or something else, I don't know. Do you have any questions for right now? Please ask if you have any. If not, we are going to end this session. Okay, I hope it is useful for you, and I'm going to wait for your comments, okay, via email Okay? See you.